Yeah, thank you. Yeah, just video. Yeah, good. Hi, thanks for the introduction. And this is a joint work with Vít Punčochář, who's also here with me today. So the goal for today's talk is relatively simple. The plan is to introduce a type natural deduction system for intuitionistic inquisitive logic, including its extended variant with presupposition modality. I'll explain a little bit later what exactly that means. The term calculus I will use is for establishing the Curry-Howard correspondence is lambda calculus extended with the new construct I call the select function corresponding to the split rule, which is the key rule of inquisitive logic. Also, we'll talk more about it later. And why I think this is interesting, because there has been some previous observations or conjecture that there is actually some sort of genuine, interesting computational content to questions, and this is sort of way how to try it more formally. So first, some background. Inquisitive logic is an intermediate logic, which means it lives between sort of intuitionistic logic and classical logic. We can think about it in broad strokes as a sort of unified framework that deals both with statements and questions, and there are also various applications to philosophy of language or linguistics. It's quite well explored from a model theoretic and algebraic point of view. There's quite nice and elegant semantics. Unfortunately, for the sake of time, I'll be mostly skipping it. Recently, there has been also some further work on sort of proof theoretic exploration of the inquisitive logic. However, what's still somewhat missing is sort of the look at the inquisitive logic from the type theoretic point of view. To our knowledge, this has not been made before, so this is essentially the attempt to provide some further insight looking from this perspective. Now, some early and brief motivation. As I mentioned at the start, there's been some sort of observations that actually there is some sort of interesting computational content to questions, which can, of course, be traced much further, going back to relating questions to problems and then to Kolmogorov or Medvedev and so on. But this is one sort of motivation, and we can do some further observations between various similarities. For example, we can encounter sort of propositions or questions as information types, interpretation native to the inquisitive paradigm, and this can be sort of reminiscent quite closely to the, of course, the well-known proposition as type interpretation native to the Curry-Howard correspondence paradigm. Also, we can draw some early links between the notion of resolution, again, native to the inquisitive framework. Resolution is essentially a way of resolving a question, meaning reducing it to its possible answers, in this case, statements. And again, this makes many similarities to the well-known BHK interpretation of connectives, meaning Brouwer-Haidt and Kolmogorov meaning explanations of logical connectives in terms of proofs. So let's take a closer look at the inquisitive intuitionist logic. So this is the language, so basic propositional one, the standard set of connectives. Just one important note: the disjunction you see here, it's actually inquisitive disjunction. What this means is essentially it's treated as the basic question-forming operator. However, it's not just a constructive disjunction as you would assume in the intuitionistic setting. What makes it special will be discussed on the later slide. As a defined connectives, we take negation in the same way as standard in intuitionistic logic and equivalence. What's the first sort of a special thing about inquisitive logic? We also separate a distinct class of formulas, which are called declarative formulas. Roughly put, they are disjunction-free formulas that play the role of statements in contrast to questions, and we can use them treat them as possible answers to those questions. So again, as I mentioned, we'll be skipping over semantics. So just let's look at a sort of inference calculus system. To obtain this sort of most basic intuitionistic inquisitive logic, we just take standard intuitionistic propositional logic and add the following rule known as split, which can be regarded sort of a rule for distributing implication over the inquisitive disjunction, assuming that actually the antecedents here is restricted to declarative formulas, the disjunction-free formulas. And this is actually what makes sort of the inquisitive disjunction special from the proof theoretic point of view, meaning is this sort of additional property specified by the split rule. Of course, on closer look, it reveals that we can treat this as a generalization of the quite well-known Kreisel-Putnam, also known as Harrop rule, which is the same. Same general idea. only the antecedent is just negated formula. So this is actually a subclass of the declarative formulas, which the declarative formulas can contain a wider range of forms. Of course, if we add Kreisel-Putnam logic to intuition logic, we obtain Kreisel-Putnam logic. So now let's move forward to establishing the Carré-Haber correspondence. From what I said, there are two main tasks for us. First, how to deal with the split rule alone, because this is the key rule that makes inquisitive logic into what it is from the proof theoretic point of view, and then how to deal with the declarative formulas which are needed to properly sort of capture the meaning of the rule. So first, the most simplistic and straightforward attempt would be simply take the rule and just essentially assign it proof terms as one would do in a sort of typical Carré-Haber correspondence fashion. So essentially, we just stipulate some sort of function split, and we essentially assume that it does what we want it to do. So meaning it takes the proof term f and it transforms it into a proof of the conclusion. Of course, this works perfectly fine in quotes. However, of course, this sort of disregards the initial motivation and observations at the beginning, meaning that there's some sort of genuine computational constructive content to question, because this way we essentially treat the split rule just as a black box which has no associated computation rules, meaning we don't know how to evaluate it. In other words, it's essentially just a constructor that's rendering as a value that has no associated way to evaluate it, and that's it. So we propose to take an alternative approach, meaning we, instead of split rule, we adopt this rule, which can be regarded, I call it this, but also be basically understood as a generalized disjunction elimination rule, because if you look at it, it's just disjunction elimination rules, but we've added these declarative assumptions, both on the major premise and the minor ones. What this allows us that we can just sort of go as the standard Carré-Haber correspondence would guide us, meaning we just prescribe the terms, which the situation is now improved because once this is sort of designed on the top of the elimination rule, meaning elimination rules introduce eliminators, and eliminator rules needs to be prescribed computation rules. So they tell us actually how the function we just introduced computes. And this opens the key sort of the problem behind this rule is essentially how to evaluate the select function. Because of course, where's the problem here? There's the complication. If this was sort of standard disjunction elimination rule, meaning there would be no additional assumption, we would just start by taking T and evaluate it to its canonical constructors, so one of the two injections, and then we would use these results to essentially run the case distinction. But of course, in this rule, as I just showed to you, there's the problem that the T itself is actually dependent on some open assumption or free variable of type alpha, the declarative one. And of course, in general, in constructed type theory or this sort of type lambda calculus, we cannot evaluate open terms to their canonical values. Because of course, so how to deal with it? First, to get around this issue, we've switched from declarative formulas to Harop formulas. What are Harop formulas? Simply put, they are slightly generalized declarative formulas, sort of like almost disjunctless formulas, because they are same as declarative formulas. However, they are allowed to contain disjunction in the antecedents of implication. We can use this fact with the following observation. Actually, for every Harop formula, there's an equivalent disjunction-free declarative formula. So this allows us to treat them as more or less equivalent. And actually, why we do this? We do this because then we can actually utilize this previously established result by Jan Smith, initially proved in the framework of constructive theory, but similar results were also achieved by Galt earlier for sort of non-type theoretical framework. And what this essentially allows us to state that no, actually open terms are not an issue. We can evaluate them to canonical forms. However, there is the one important sort of side note that the open, the free variables, which those open terms contain, has to range over Harop formulas and Harop formulas only. If they do, it's fine, and we can actually evaluate them to canonical forms despite these Harop-shaped holes. So utilizing this, we can just slightly tweak the generalized disjunction elimination rule by replacing the declarative ones for Harop formulas, and then we can proceed and specify the computation rules, which take the following four. and it works quite nicely. Now, in the rest of the time, because I'm slowly running away, so just briefly, we consider a sort of extension of the system I just introduced with the additional presupposition modality. So what are presupposition? Strictly speaking, just informative contents of a question, meaning, for example, if I ask you a question like, who spilled the milk in the coffee room? I'm already giving you some sort of information, meaning there is a sort of spilled milk in the coffee room. We capture this via the modality we call presupposition, and then on the circle that turns actually the inquisitive formulas or questions into declarative ones. And this is sort of loosely inspired by truncation, where because you can use truncation to, or propositional truncation to be more specific, to turn arbitrary types to mere proposition. Here we are turning questions into sort of declarative ones, the presuppositions of those questions. So we just extend the language with the circle modality and then associated constructors and eliminators. The introduction rule looks as follows. Again, it's if you're familiar with proposition truncation, you definitely can see some similarities. Again, just one extra note. Note that both the conclusion of the hypothetical premise as well as the conclusion of the rule itself is restricted again to just Harrop formulas. So this sort of echoes the restriction to mere proposition with truncation elimination rule. Computation rule looks as following. And if we add these to the original system, we obtain the sort of modelized variant of the inquisitive intuitionistic logic. One more important note, once we actually adopt this modality, it sort of destroys the nice relation between declarative formulas and Harrop formulas, because by definition, the modelized formula is still declarative. However, it's no longer Harrop. So this is still something to go through and look how could this be fixed or circumvented. So just conclusion, final remarks. As I mentioned, inquisitive intuitionistic logic is intermediate logic, which I think this makes it quite interesting by providing like fully computational and constructive Curry-Howard interpretation for it. Because of course, traditionally the idea is that sort of the intuitionistic logic and constructive logic are more or less synonyms. But this shows that actually no, that constructivity extends beyond just intuitionistic logic and creeps into the realm of intermediate logics. Also, I haven't time to speak about it, but the system is actually normalizing and it has disjunction property and other nice technical results. Concerning future work, it's mostly just to deal with possible other variants of the split rule itself. For example, fully schematic variant, meaning we can drop the restriction either to Harrop formulas or the declarative formulas and use the presupposition modality instead, which also turns them to declarative formulas. We can also consider unrestricted variant, meaning we drop also even the presupposition modality restriction and obtain a sort of the unrestricted split rule, which then leads to actually a Gödel-Damet logic. And finally, it's to also consider first order variant of the rule, which is a sort of variant where instead of the disjunction that what plays the key role there is the existential quantifier, and then of course leads to first order inquisitive logic, but it's also still things to do. So yeah, that's everything. Thank you very much for your attention.